Quantum mechanics governs 99% of the universe's particles, yet only 1 in 1,000 physicists fully grasp its implications. A 2018 study by University of Cambridge found quantum coherence in bird eyes, defying classical physics models. But your brain uses the same quantum processes that Einstein called spooky action at a distance. Niels Bohr slammed his chalk down at the Solvay conference in 1927, shouting, "No, Einstein, you're missing the point." This moment would define whether reality itself, whether atoms, light, or consciousness, was fundamentally probabilistic or deterministic. Quantum mechanics began with Max Planck's 1900 discovery that energy comes in discrete quanta, not continuous waves, a radical idea that shattered Newtonian physics. Planck's work, though initially dismissed, earned him the 1918 Nobel Prize, yet he privately feared he had opened a Pandora's box. A decade later, Albert Einstein, then a patent clerk in Bern, proposed light behaves as particles to explain the photoelectric effect. His 1905 paper was so radical that many physicists ignored it until 1923, when Compton's experiments confirmed Einstein's vision. Niels Bohr, inspired by Planck and Einstein, built his 1913 model of the hydrogen atom, with electrons orbiting the nucleus in discrete energy levels, a theory that finally explained spectral lines but left Bohr uneasy. The final piece came in 1927, when Clinton Davison and Lester Germer, working at Bell Labs, fired electrons at a nickel crystal and saw interference patterns, proving electrons behave as waves. This double-slit experiment, echoing Thomas Young's 1801 work, confirmed wave-particle duality, a cornerstone of quantum mechanics. Yet even as the theory took shape, physicists like Einstein grappled with its implications, asking, if light is both particle and wave, what does that say about reality itself? The Copenhagen-interpretation, championed by Bohr and Heisenberg, declared that quantum systems exist in superpositions until measured, a concept Einstein famously called spooky action at a distance. At the 1927 Solvay conference, where physicists gathered to debate the new theory, Einstein challenged Bohr with a thought experiment. If two particles are entangled, measuring one should instantly determine the state of the other, violating relativity's speed limit. Bohr, ever the showman, countered with a lecture on complementarity, arguing that quantum systems defy classical intuition. The debate left the audience in awe, though Einstein left unconvinced. His frustration culminated in the 1935 EPR paradox, co-authored with Podolsky and Rosen, which argued that quantum mechanics was incomplete. They proposed hidden variables to explain entanglement, suggesting particles carried pre-existing properties, like secret notes, that quantum theory failed to reveal. Bohr dismissed the paper as a profound misunderstanding, but the EPR paradox ignited decades of philosophical and scientific warfare. The battle reached its climax in 1964 when John Bell, a physicist at CERN, devised a theorem that could test Einstein's hidden variables. His inequalities, derived from quantum mechanics, predicted that entangled particles would exhibit correlations stronger than any classical theory could explain. In 1982, Alain Aspect and colleagues at the University of Orsay conducted experiments using entangled photons, confirming that Bell's inequalities were violated. The results were staggering. Quantum mechanics wasn't just incomplete, it was fundamentally non-local. Einstein's dream of a deterministic universe crumbled. Yet the Copenhagen interpretation still held sway, with Bohr's disciples insisting that reality only solidified upon measurement. But what if the universe wasn't probabilistic but simply beyond our grasp? The question lingered unanswered as physicists like Schrödinger and Heisenberg grappled with the implications. In 1935, Schrödinger's thought experiment, a cat both alive and dead until observed, mocked the absurdity of superpositions. Heisenberg, meanwhile, saw the uncertainty principle as a fundamental limit of knowledge, not a flaw in reality. The war between Einstein and Bohr had ended, but the war over reality's nature had only just begun. In 1957, while working as a defense analyst at the Pentagon, Hugh Everett Fee scribbled a paper in the margins of a notebook titled Relative State Formulation of Quantum Mechanics. His radical idea, every quantum possibility branches into parallel universes, each existing simultaneously. It was a theory so alien to the physics community that it was nearly discarded until John Wheeler, Bohr's protégé, saw its potential. Everett's many worlds interpretation suggested that the act of measurement didn't collapse a quantum state, but instead split the universe into countless copies, each hosting a different outcome. To Einstein's contemporaries, it was madness, yet here was a way to avoid the Copenhagen interpretation's spooky collapse, preserving determinism without invoking hidden variables. But the Copenhagen camp wasn't ready to surrender. Werner Heisenberg, ever the pragmatist, argued that the uncertainty principle wasn't a limitation of knowledge, but a fundamental feature of reality. In 1927, his formulation showed that measuring a particle's position collapses its wave function, making precise predictions impossible, a direct challenge to classical determinism. Heisenberg's uncertainty wasn't just a technical hurdle, it was a philosophical rupture. If you couldn't know both a particle's position and momentum with certainty, what did that say about the nature of reality itself? Enter Schrödinger's cat, a thought experiment designed to mock the absurdity of quantum superpositions. In 1935, Erwin Schrödinger imagined a cat both alive and dead until observed, a paradox meant to highlight the Copenhagen-interpretation's flaws, yet the many-worlds theory offered a chilling resolution. In one universe, the cat lives, in another, it dies. No collapse, no paradox, just an infinite proliferation of realities. The measurement problem, once a thorny debate, now became a question of which branch of the multiverse you happen to inhabit. But here's the kicker. No experiment has ever confirmed many worlds. It's a theory that predicts everything and explains nothing. A ghost in the machine of quantum mechanics. And yet, for all its strangeness, it's the only interpretation that avoids the Copenhagen interpretation's measurement problem without invoking magic. The debate rages on because if reality is a web of infinite branches, what does that say about free will, consciousness, or the very fabric of existence? Quantum computing's promise has grown from theoretical musings to a 2026 frontier, with companies like IBM and Google racing to build scalable quantum processors. Yet even today, decoherence, the relentless interaction of quantum systems with their environment, remains a thorn in the side of engineers. In 2026, a breakthrough by researchers at MIT and ETH Zurich revealed that error rates in quantum gates could be slashed by isolating qubits in near-perfect vacuum chambers, a technique inspired by the 1980s work of William Unruh on quantum fluctuations. But practical quantum computers? They're still a decade away, their promise tempered by the fragility of superposition. Paul Dirac's 1928 equation, which unified quantum mechanics with special relativity, predicted antimatter, a discovery that stunned the physics world when Carl Anderson identified the positron in 1932. Dirac's work earned him the 1933 Nobel Prize, though he privately wrestled with the implications of a universe where matter and antimatter could annihilate each other. His equation, a masterpiece of mathematical elegance, also hinted at the existence of magnetic monopoles, a mystery still unsolved a century later. Why does quantum mechanics govern atoms but not tables or trees? The answer lies in decoherence, the process by which quantum systems lose their coherence when interacting with the environment. In 2026, a team at the Max Planck Institute demonstrated that even a single photon scattered by air molecules could collapse a quantum state, a phenomenon likened by physicist Wojciech Zurek to a wave in a pond being disturbed by a pebble. This explains why macroscopic objects behave classically, quantum effects are drowned out by the noise of the world. Yet the deepest questions remain. If reality is probabilistic, does that mean free will is an illusion? If the many worlds interpretation is correct, are we just one branch of an infinite multiverse? These are not abstract riddles, but the very heart of quantum mechanics, a theory that has rewritten physics, yet leaves us staring into the void of what we do not know. The legacy of quantum mechanics is not just in its equations, but in the way it has reshaped our understanding of existence itself. From Planck's quanta to Schrödinger's cat, the theory has forced us to confront a universe that defies intuition, a realm where particles are waves, where observation alters reality, and where possibilities multiply like branches on a tree. It has birthed technologies that power our world, semiconductors, lasers, and the very computers you're using to read this. Yet its greatest gift is not practical but profound. It has taught us that reality is not a fixed stage but a dynamic, participatory act. Behind every equation stood a human. Planck, who feared his work would unravel the cosmos, wrote in his journals of a horror of quantum mechanics as he grappled with its implications. Einstein, ever the rebel, spent decades battling Bohr over whether the universe was probabilistic or hidden. Heisenberg, in his 1927 paper, didn't just write mathematics. He wrote a manifesto about the limits of knowledge. And Everett, the lonely theorist who proposed infinite parallel worlds while working in a Pentagon office, left behind a legacy that still divides physicists. These were not cold minds calculating. They were dreamers, skeptics, and visionaries wrestling with the unknown. But what does it all mean?